of the other areas. For example, tool marks. A tool mark is a specimen that is the result of contact between a tool and a surface, but the coming together of the tool and the surface is through the action of the tool being used. So as a result, you're either going to get a cut, a gouge, scrape, something like that effect. So there are only two types of tool marks that you can have. Now we have three physical patterns. We have imprint, indentation, and striation. But for tool marks, we only have two. We have indentations and we have striations. You cannot have an imprint that is categorized as a tool mark. You can have an imprint of a tool, but that's not a tool mark because the tool was not used in any action to create it. If you had a screwdriver that had grease or blood on it and it fell on the floor and had a very nice impression of that tool on the floor, that's an imprint of that tool. It's not a tool mark because the tool is not being used in the manner that we would expect to use the tool. So an indentation is created when you exert pressure and then leave the impression of the tool in a softer surface. Remember, indentation is a hard surface contact with a softer surface. So if you, for example, I have a ruler, pretend it's a knife or a screwdriver, and if I want to stick it between two surfaces, like in here, and then I want to pry open a door or a window, I am compressing it against the softer surface to try to open it. In doing so, I'm going to leave the indentation of the screwdriver in the wood. That's an indentation. And this action is referred to as a prying action. It lets us know what action is being taken by the suspect. It's part of putting that hypothesis together, not just that there's force entering, but what's the manner of force entering. Then we have striations. Striations, remember, occur when you have two objects come together and one or both are moving. So now, by the way, quite often you have these two together in a tool mark. So now we take the screwdriver and now I need to force it in to an area. So I'm going to slide it and then I'm going to compress. Sliding action of the tool against the wood is going to have the wood being pushed. It's going to have scratch marks. You may, depending on the surface that it's on, you may not be able to really tell what the tool is. If you have two of these combined, you will have a striation from the pushing of the wood. But then at the bottom, deep in the mark, is your indentation. So you will actually have a combination of the two. If you have a tool that is going against perhaps a window frame, which is metal or vinyl, you're going to get scratches on the surface. Scratches can be compared. See where they are. So here you have scratches, striations that were created by a screwdriver, I believe. And you have them sliding across a metal surface or a plastic surface. You can actually see the grooves from the actual tool itself. Now, when you examine any type of tool mark, the first thing to remember, of course, is to never place the tool into the tool mark to see if it fits. And that is a very tempting thing to do all the time. We do not do an examination by placing the tool into the tool mark. If you do so, you have inherently changed the mark. It now will resemble the tool that you just placed in it. And while you say, well, I just kind of placed it in there, I really didn't do anything, it doesn't matter. Legally, you compromise this specimen by doing that. And that specimen will be thrown out and not have any worth in the case whatsoever. All right. So the first thing you're going to do when you examine a tool mark, by the way, the striation is a gouging action where the indentation is prying action. So the first thing you want to do is examine for any loose material in the mark itself. And if you are at the crime scene, you have to cast the mark because you cannot remove the item which it is contained within. If you have a door frame, you should bring in the door frame. The only time that you would cast it at the scene is if you can't do that. If you have a mark, if you have a lock, you have the metal frame on the door, bring the metal frame in. Because one of the first things you need to do when you have an indentation, especially striation is not as critical, is to examine the mark for any foreign grain. It is likely that perhaps a chip from the tool broke off in the mark, particularly if you have a gouging and then an indentation compression action being used. If we can find a piece of the tool in the mark, we can do a physical fit. A physical fit is an absolute comparison, unlike this. This is not that specific. Then you are going to diagram, and you are going to measure. And when you measure any item, I have found this in the last couple of semesters, that students think when you measure something, you're only measuring length and width. Probably gonna have to say this more than once. Length and width is not enough. If you tell me, because you have a lab, you're going to be working smart this day, halfway through this lab, and you have to measure things. If you give me length and width, it will be wrong. Because the objects that you are looking at have more than one dimension to them. They have a perimeter edge. If you have an object that has 4 different sides, and it's not square, there is no length or width. There are 4 different measurements that need to be taken. So get it out of your head right now. Length and width is not a measurement that we're looking for. We need every single dimension. And I am more interested in the perimeter measurements than I am the area measurements. Because we are trying to physically fit something back together. I need to know how big the opening is versus how big the item is that you're trying to put into it. And if you just give me length and width, that's not going to be sufficient. This to me means lazy. Okay? So get that, whatever you've been taught in math before, length and width is not the end all be all to measuring things. Okay. You need to diagram the item, and when you measure an item, you put the measurements right on diagram. This is why we must diagram our specimens in addition to photographing them. Because you can put information on a diagram that you can't get into a photograph. Okay. You can be much more specific in your comparison for that. Okay. Then we are going to describe the mark. And when you describe the mark, you cannot say it looks like a screwdriver. Stating that a tool mark looks like a flathead screwdriver is a conclusion. It's not a description. You have to first state, what does that mark look like? Right? Is it rectangular? Okay. You could have a straight edge with straight sides that then angle in toward what appears to be a rod, right? A singular thing. But you cannot call this a screwdriver. As painfully obvious as that may be. You have to identify it first. You have to describe it. Because my question, if you say to me, well, it looks like a flathead screwdriver, then I'm going to say to you in court, well, what does a flathead screwdriver look like? So you're going to have to describe that anyway. So you might as well do it correctly the first time. Right? And the defense attorney is going to argue the fact that by stating a flathead screwdriver, you're already making a conclusion. And your conclusion is based on what? Shape? Okay, well, what's the shape? Well, you don't have it written in your notes. So how do I know what you're basing that conclusion on? Nothing, because you don't have it documented. Right? So always remember to not jump the gun and go right to identifying the specimen. You have to think in terms of describing its shape, its color, its width, all of its characteristics. Then in the end, you can say that in your opinion, this was made a flathead screwdriver. And that can be from your own personal knowledge. A lot of people don't know what a flathead screwdriver is. A lot of people don't know what a Phillips head screwdriver looks like. Right? That's the star-shaped one. Okay? Then we are going to describe the action that was used to create this mark. Is it an indentation? Is it a striation? That indicates the action that was used. You're going to note anything unusual about the features of this mark. Is it broken on one side? If this is an indentation. Right? If it's a striation, the picture you're looking at here, the unusual features is you have this gap here on the mark. Then you need to make a substrate control, because we cannot put the tool into the mark. And this is really important if you have a striation, because your examination is just scratch mark. You need to take your possible control sample, your exemplar, and you need to recreate the mark. If it's an indentation, you need to make an indentation. If it's a striation, you need to make a striation. And then you need to compare the two samples together, not the sample, not the tool mark, and the tool. The two tool marks, one that you have as a specimen and one that you created. And that's what we have in this picture. One is the actual sample, and the other is the control. This is a photograph of a comparison microscope where you have the two samples on two different microscopes, but the two microscopes are connected with one ocular. so that you can butt them up next to one another without physically doing it, which is great because we don't have to have the ends of the metal together. We can put it in the middle because we can place our specimen on the microscope anywhere we want. This line running down the center here, this is your demarcation between the two microscopes that you're looking at. And you can see by looking at this photograph here that they are indeed have continuity of pattern, which is your comparison process for striations. Once you have all of that now comparison done, you'll draw a conclusion as to whether or not this tool could have made the mark. And the majority of the time, the furthest you can go in your conclusion is that it could have or could not have. Eliminating is a lot easier than specifying. The reason for this is striations are a little bit more definitive in identifying a specimen. Indentations, not so much. It looks like a flathead screwdriver. Okay, it's a 1-inch flathead screwdriver that separates us from 2-inch, half-inch, quarter-inch, so on. But there are still thousands and thousands and thousands of 1-inch wide flathead screwdrivers. So unless there is something unusual about this particular mark, you cannot say with absolute that this tool made that mark. It's just a could have. Now, if you're found right on the property and you have this tool in your back pocket, and this is the tool, a similar, just like this tool we've determined was used to break in, well, that's for the jury to take that a step further and decide that, yeah, you're the one who did it. That's not up for us to do. Remember, forensic scientists do not determine guilt. We don't care. We are simply connecting items together to determine whether or not they are the origin of the evidence that we are observing. Ballistics. What is ballistics?
Ammunition.
And
The forensic study of ammunition.
the gun. The gun. In order to examine bullets, you need to have the gun. All right. So when you have a gun, when they do ballistics analysis, most of the point is to determine whether or not a bullet was fired from that weapon. So what you are comparing is the bullet to the barrel of the gun. Right? So if you, for some reason, thought you were going to be caught for a crime, if you switch out the barrel and place it on another gun, and somebody says, well, it was so-and-so's gun. If you switch out the barrels, you might try to confuse the police, but not really, because what they are examining is the barrel, not the weapon. So if you say, well, you own a gun, and so now they want your gun, and so you hand them your gun, but you switched out the barrel, they're not going to be able to trace that back to you because you switched out the barrel. Now, you get somebody that's really good by examining the gun, they'll be able to tell that you actually did that. So we'll see. So when you have the barrel of the gun, this is a solid piece of metal that is hollowed out with a drill, and that is called a broach gun. when they hollow out the barrel of the gun, drills spiral, right? As they're working their way through this piece of metal to hollow out the actual bore of the gun. In the process of doing that, there are what we call lands and grooves. We've given them names. Scratches that wind up on the inside of the barrel of the gun.
Sorry, you're blocking the other name. What's the other name too? Groove and what?
Lands.
Oh, thank you. You said that was the scratches in the barrels?
They are. I'm trying to pull up a picture. Anytime you have two pieces of metal come in contact with one another, you're going to have scratches made. I'll find this eventually. And inside the barrel of the gun, I can't find it. Okay. So the lands and grooves are like hills and valleys in the barrel. So there's parts that have like plateaus to them, and then there's parts that are more recessed. When the bullet is fired from the weapon, these lands and grooves make the bullet spiral. They were first there by accident. They didn't know they were there. And then they realized what they did. Right? And that is called rifling. Now they put the lands and grooves there on purpose. Different manufacturers have different numbers of lands and grooves. Smith & Wesson has 5. Colt has 6. Some manufacturers, depending on the model, it may twist to the right. Some may twist the bullet to the left as it passes through the barrel. Someone who is an expert in ballistics can look at the bullet and actually tell you which it is, and many times be able to identify the actual gun manufacturer on how many lands and grooves are actually there. Okay? What is caliber?
Isn't that how big the bullet is?
It's the diameter of the barrel, correct?
Okay? It is how big the bullet is, but more specifically, it is the diameter of the bullet. It is also the diameter of the barrel of the gun. So when we have 22 and a 38 and a 45 and a 50 caliber weapon, what does that mean?
That's how big the barrels are.
But what does it mean?
The bigger the bullet, right?
But what does that number mean? Why did they choose 38? Why not 40?
The millimeter, so 22 millimeter is the
Ammunition.
diameter of the bullet.
No, close.
The barrel, the diameter of the barrel.
Not
The ammunition.
not centimeters.
Millimeters.
No. What do we use? inches. These numbers correlate to how wide the diameter is of the bullet in inches. Now, it's not 22 inches. It's 0.22. It is 0.38, 0.45, 0.50. So a 22 is slightly less than a quarter of an inch. 38, a little more than a third of an inch. 50 caliber bullet, that bullet is a half an inch wide. That's why it hurts when you get shot. That'll kill you. Now, if you have a 9mm weapon, the bullet's diameter is
9 millimeters.
9mm. That's why they specify 9mm versus just saying 38, 45, and so on. The understanding is when I say 45, it is 0.45, but nobody includes the point part of it. Now, there are 25.4 millimeters for every inch, right? Because everybody always knows 2.54 centimeter equals an inch. So 25.4 millimeters is an inch. So 9 is somewhere between a 38 and a 45 in size. Okay. Now, when you do a ballistic comparison, you can look at the bullet, but you can also look at the casing, which is why they always want to collect the casing, the cartridge case that the bullet came in. There are scratch marks that occur from the firing pin. That's what sets the whole chemical reaction in process. So you can see here we have on the right, a sample and a control. This is our line of our comparison microscope. And you see all these scratch marks. Every single one of them continues from left to right. That is continuity of pattern. And the only way both of these shell casings would have the exact same scratch pattern is if they were fired from the same weapon. And that's how they do ballistic. Very simple. Here we have a bullet that is being compared to a control. We have A, B, and C. By the way, IBIS, this is the database system. It's the International Ballistics Identification System. All of our databases have acronyms to them. Okay. So when you do a ballistics analysis, you have to be able to spin the bullet. So it's on a pressure point that allows you to do that. It's not like a microscope that has a flat stage for a glass slide. This you need to have a big fat bullet get underneath it. So you need to be able to revolve it. So there's going to be different areas that look similar. And as you can see here, particularly in the second one here, all of these characteristics are continuous from one side to the other. So therefore, it did indeed come from that weapon.
Professor, I have a quick question.
Mm-hmm.
I don't know too much about guns, but if a bullet gets stuck, and if the suspect or whoever was to remove that, will that change any of like the scratches that would be on the bullet?
Absolutely. They've tried doing that often, they will actually try to just put some type of a metal rod in the barrel of the gun to actually obliterate the lands groups that are in the barrel, so then you can't do a comparison.
Okay.
Sure. Oh, the bad guys, they know all this stuff, which is why you may have somebody that will switch out the barrel so that when you come looking, if I'm the husband and I killed my wife, well, I own it. You're going to know I own a gun because they're supposed to be registered, right? Notice I said supposed to be. So I'm like, oh, I shot my wife with my gun. So what you do is you get an illegal gun, and then you switch out the barrel. And then when they come to recover your gun, the serial number is on the handle of the gun, not the barrel. So then you'll be able to determine not a match, which is what you want, but then eventually they'll be able to figure out that you switched the barrel. I don't think they've done it yet, but there is a push to expand the database for ballistics, that every weapon, when it's manufactured, a ballistics identification is automatically taken before it's even sold and is uploaded into the database, so that anytime a weapon is used illegally, you can automatically identify the gun and hopefully be able to trace its ownership. Now you need to be able to get the gun to do a comparison. There is no set database for that. I know that.
But would that database only be beneficial within like the United States, or would that kind of be like worldwide? Because I know some people purchase firearms from different countries.
That would control American companies.
Okay.
So Smith & Wesson, if they sell things overseas, they're still mandated by laws here. If your company is here. So if you have some German manufacturer, well, they're going to thumb your nose at American laws. They don't care, right? So you go buy a German gun. There's ways around everything. The government can mandate you to death, but people will figure out a way to get around it. Right? So, it doesn't do anything. And that would help with stolen guns, because the database will follow the gun, right? Whether it's sold legally or illegally, because that will be in the system before the gun was actually sold to anyone. As soon as it was manufactured, then that ballistics analysis would be in there. But as we all know, there's millions and millions of guns out there that they have no idea what they're from. They have millions and millions of guns that aren't even registered, okay? And they're not going to get registered. Okay? They can say as much as they want for people to turn all their weapons in. Yeah, that ain't happening. I don't know anybody that owns a gun that's going to turn their gun over to the government just because they said so. Not happening. Okay. So the analysis of ballistics, of course, is continuity of pattern, because these are striations. Now, one other thing we can do is to reconstruct serial numbers. It's really not a physical pattern, but I like to throw this in here. Is it possible to recover serial numbers that have been scratched off?
Probably, depending on how they scratched it off.
That is true. Okay? It depends on how well you scratch it off. If you were to scratch off numbers, how well would you do it? How far down would you go?
Well, I would make sure that I would scratch from the top of the number down to the bottom, from left to right, to make sure it's an even scratch.
Okay. So you would scratch it to the extent then that you can't read the number, right? If I can't see the number, if I think I've scratched it down to a certain level surface, and the number is gone, is it?
No.
No, of course not. We have our ways. When they imprint numbers, serial numbers, on an item, particularly if it's in metal, and that's usually where they put it. It's kind of hard to put it in plastic. When they do that, you use a very high pressured press. Now, in chemistry, in molecular structure, molecules are very oriented. They are all in a nice crisscross fashion, very nice, forming together. When you compress the numbers, you actually slightly alter the molecular structure of the metal at that point. So the molecules are actually pulled closer together. So when you scratch off the numbers, you only do so to the point where you can't see it. And that's what most bad guys think. That if I can't see it, it's with a lot of stuff, but if I can't see it, it's not there. It's gone. I got rid of it. You can't see it. However, using chemicals, we can get the chemicals into the metal that has been overly compressed, and we can get the numbers to reappear. Now, if you've taken a drill to the serial number and really gone deep into the metal, it is very likely you will have removed them. But most people who are trying to remove serial numbers don't do that. They only just scratch it until it's a mess, and then you can't see anything. It's a very simple process. Now, there are different types of chemicals to use, depending on whether you have zinc, alloy, which is steel, whether you have aluminum, whether you just have tin. But most guns are a zinc alloy, which is your steel. So I'm going to give you the method for doing that. And this is the method that the ATF, the Alcohol, Tobacco, and Firearms Federal Agency, this is the method they use to recover serial numbers off of guns in particular. So we have two solutions that we're going to do. One, we have a solution that is 98 milliliters. This is one. Let me see what it is. 85% phosphoric acid. And 2 milliliters concentrated nitric acid. So pretty strong stuff. So what you're going to, believe it or not, do to your gun that's had the serial number scratched off is, believe it or not, you have to take and you have to file it down even more. You need to file it down until you have a smooth surface. And then you need, of course, to clean that off. Okay? So you don't want to have any rough surfaces. You want to have a nice flat surface. We're going to take this solution and we are going to pour it onto the area. You're going to put like a clay dam around it and clean the area. So this gets all of the excess metal out of there, right? And it starts to burrow down into where the numbers are actually compressed. The numbers being compressed actually absorb the acid more so than the molecules that have not been compressed. Right? So the numbers will absorb the acid, the surrounding area will not. We then take a solution of 10% nitric acid and swab it on. So you have a cotton swab, and the action of swabbing it is actually what gets the acid now into the letters. After about 2 minutes, the letters will turn white and the resulting background will be gray. And you will now be able to read the serial number. Now again, if you gouge them out too deeply, we can't recover them. But even though you can't see it, the action of compressing the numbers changes the molecular structure further down in the metal than physically what you can see and feel the numbers being indented. Okay? It goes beyond the actual indentation. So people scrapped out just the indented part, but the actual number goes down a little bit further, and that's the part that is actually absorbing the acid more so than the actual metal that's not been disturbed at all. This is the method they use on guns. And it had one particular week, they had about 185 guns that they had to recover the serial numbers for, and they got 100% recovery in about 8 hours. All 185 guns that they did. Okay? Okay, let's see what time it is. Doing good. Okay. Now, let's talk reconstruction. In reconstruction, we are always, of course, interested in the evidence we find at the scene. But when you have evidence that involves scene reconstruction, it is important for you not to remove the evidence yet. It is important for you to recognize that where this evidence is more important than identifying the evidence itself. Examples of where we do reconstruction. Glass fracture, which is why you have glass up on the screen for you. When you have glass found at a scene, don't automatically start picking it up. You need to identify exactly where it is, potentially how it got there, where it potentially came from, and the circumstances as to why it is where you see it. If you have a door that has a window pane that is broken, and the glass is on the inside of the door, what is your conclusion with that?
That someone punched the window from the outside?
Logically, that's what you would think. But sometimes people stage a break-in. What if they took a piece of cardboard, put it in front of the window of the door, and then broke the door, but all the glass fell inward because you had that piece of cardboard? Seems kind of dumb. Why would you do that? There are people that do that if they stage the scene. So you may have the circumstance where we need to determine from which side the glass was broken. So don't be so quick to pick it up. If we have the instance where it's snowing, you have a bullet fired through a window. And the question is, did the bullet come from inside the window or outside the window? So maybe you have somebody that was shot and then a bullet hole in the glass. Well, we need to determine whether or not this was a misfire from inside or did the bullet come from the outside. So we need to examine the glass itself. There it is. Don't be taking it out because then we won't know necessarily which side of the glass is which. So one of the first things that you will look at, first of all, when you have glass at a scene, the first thing, once you collect it all for us in the lab, what the first thing we do is put it all back together. It is important to put all of the glass back together because you may have a piece that's missing. And if you have a piece that's missing, where might that piece be?
On the suspect.
On the suspect. All right. So while we can do and will do, what's later, glass analysis, but glass is, is in different categories is very common. It's very difficult to specify that this actually came from you, right? Because glass is glass, unless it's something that's uniquely made. We want to try to physically fit it back together. So if we can put the glass back together and you find a piece on your suspect, physically fit it back. We don't have to do glass analysis. Why waste our time? We have absolute proof that these things were once one, doing physical matching. Okay. Now, when glass breaks, when anything strikes glass, the glass actually moves, so it actually goes forward. You have all of the energy of the force traveling through the glass, and then because the glass bows, it actually breaks on the side opposite the force. Then it decompresses again, and then the second cracks that form are on the same side of the crack. Now, when you have something break, these cracks that form opposite the force radiate outward from the point of impact. And because they radiate out from the point of impact, we call these radial cracks. They are the first to occur, and they always occur opposite the side the force originated from. Secondary cracks then occur on the same side of the force, and these will then go around. And they're not attached to each other. Okay? They're just secondary from each of these radial cracks. And these are called concentric cracks because they go around in a circle. They're attempting to hold the glass together, actually. Now, when the glass cracks, the crack goes all the way through. So one feature to always keep in mind is that one crack cannot pass through a pre-existing crack. So that's why these concentric cracks are individual cracks. They're not one solid circle going around, even though they may appear to be roughly in the same area. They can't pass through the radial cracks, and radial cracks occur first.
Professor,
Yeah.
can you just please repeat that one last time? You said that the cracks cannot pass through another set of cracks, correct?
Correct. When you
Okay.
have a crack in glass, it will stop at any pre-existing crack. The cracks go all the way through the glass. They're not just on one side, they go all the way through. And it's instantaneous. So the radial cracks will occur first, followed by the concentric. These are actually in between the radial cracks. They are not one complete circle. Okay? Now, when you look at the hole, you should see a cone shape, like in this picture. So looking at this cone shape, you have it where it actually so here's your point of impact. Quite often at the actual point of impact, there will be a very small hole, if any. Now, if you have a bullet goes through, it's going to create a nice round hole, like in this picture. But then what happens is the glass breaks here, so you end up with this cone shape. The smaller side of the cone is generally your entry point. That's the side from which the force originated. Okay. So sometimes you'll need to know by looking at that bullet in the window, is it just a rogue bullet that went through the window, or did it actually come through the window because we got a dead guy laying here in the floor? So looking at that glass in the photograph there, did the bullet come from the side facing you, or is it on the back side of the computer?
Back side of computer?
It came from the back side of the computer. Yeah, because the hole is here, and then this whole area here is our cone shape spreading out. All the damage, always, basic law of physics. It's when somebody gets shot, they have a small hole, the entry, they have a large hole at the exit. All of the energy goes with the bullet. You have it piercing through, so there's very little damage. And then as it slows down, it expels all of its excess energy. And that's what creates all the damage. Right? Now, that doesn't happen all the time. Well, first of all, we'll do this first. Now, when you put glass back together, you can't rely on that cone shape all the time, particularly in glass, because glass is very fragile. And if it falls, this may chip further, in which case then I can't tell. Now, if it's still in the window, that's easy to tell because it hasn't received any further damage. But if it's on the ground, you don't want to rely just on this angle here for me to determine which side it came from, because the angle may be very slight if it's anything other than a bullet hole. Okay? If somebody just took a hammer and hit the glass, the angle is going to be very, very slight difference between the two sides. So what we have to look at instead are what we call tackle marks. or conchoidal marks.
Does it matter which one we use in case we need it in the lab or anything?
I always just call them hackle marks. Let me see if I have this picture. They don't have it in the book. No, they just have a picture. Okay. We're looking at these marks here. Okay. When the glass fractures, so this is the impact point. When the radial cracks first occur, and the glass is going to fracture from this point, okay, it actually comes, there's stress marks that occur on the glass. Okay? And they start at the point of impact, and then they will slide down the glass, and then they go across to the concentric crack. And that's what then causes the concentric crack. Now, these called, that some, it depends on the book you look at, they call them conchoidal marks. And on the conchoidal marks, there are hackle marks. I just prefer to call them hackle marks. That's what I've always called them for 30 years. Right. So that's what I like. So the point of impact, because of the radial crack, there are stress marks that occur in the glass. And they come down, and then they swoop across to eventually crack the glass on the other side, the concentric crack. So they come in and do this. Wrong way. That's where we have it. So let's say the impact comes from, all right, this direction. All right. Comes in this direction, so it's going to come this way, go across, and then down. Stop and think for a second. The stress marks were not there prior to the glass being broken. They are a result of the glass fracture. Okay. So by looking at these hackle marks, because when they have certain books describe this, they'll call these conchoidal, the whole thing, and then they say there's hackle marks on them. I just call the whole thing hackle mark, because that's what I was taught originally. So by analyzing these hackle marks, we can determine with accuracy which side this glass was fractured on. And we're going to use what is called the 3R rule. The 3R says that the radial cracks form right angles on the reverse side of the force. R. So we're going to look at these stress marks. They were created by the radial crack. The radial crack formed a right angle. The right angle is here. edge of the glass, from where this comes in, is creating the 90-degree angle. So if the 90-degree angle is on this side, and the force is on this side. So looking at the picture in the book, we have apple marks coming in from this side, on the left, swooping across, coming down. They're actually starting in the bottom here. They swoop up and go across, because they start here at the point of impact, up and across. But if this is our edge of the right angle, straight edge here and then going across, the right angle is on this side. Therefore, the force came from this side. Okay?
Would it be inaccurate to say, okay, so you know how the lines, the orange lines that you have are facing the opposite side of the right angle? Would it be inaccurate to say that?
Well, a lot of people say, well, why don't I just say that the force came from the back side of his thing? Oh, you could say that. Sure.
So say that it was, sorry.
No, go ahead.
Say that those lines are facing the other way. So then does that mean that the force then came from where the right angle is now?
So they're coming from here. This is the glass. So this now is your 90-degree angle. So the force came from here. So, some people say, why don't I just say it's on the back side of the curve? Well, you can say that, because it is. But if in the moment you want to say, which side was it? If you always remember the 3R rule, you'll know which side is which. Instead of just remembering it's the back side of the wave, there's a way to figure it out. You always come back to the rule, and that gives you an accurate representation. Okay? Does that answer your question?
Yes, thank you.
Okay. So, the rest of reconstruction involves gunshot residue, and it involves blood spatter. But we're going to come back to that on Friday. Right now, I want to do lab 3 with you. We did 4 on Friday, but I reversed them. And now we're going to do 3. Right. And much of it you can do on your own. Okay, there are 3 parts to lab 3. Part A is all hypothetical. It's nothing for you to actually examine. Right? So, hold on one second. Okay. So, we just did this. First step to analyzing broken glass brought into a crime scene, into the lab, is to put all the pieces of glass back together. To accomplish this, you need to determine for each piece which side of the actual physical glass is the outside versus the inside of the glass? What characteristics would you use to determine the inside versus the outside? Think pure logic. What would you use?
I guess if there's any like dirt marks, it would be outside.
What would be outside?
It would be the outside part of the window if it had like dirt stains or something.
Yeah, it would be dirty, would it not? It would. Okay. Told you, just think logic. Okay. It would be dirtier. It would be scratched. It would be pitted. You know, if you have, things hitting the glass. Last couple of days with the snow and rain and stuff, things hitting the window, ice hitting the window. Just like that. Perfect logic. Okay. Then the question comes to be, now that you have the window put together, what characteristics would you use to determine from which side of the glass the bullet was fired from?
Look at the radio cracks.
What would you use first? You have a bullet hole in the window. The window's not necessarily broken. You just have a bullet hole in the window. What would you use?
Could you use the cone shape method?
I would. Okay. So you would list the characteristics related to that. Then you have this diagram. And the question is, and these templates, by the way, are all on your lab assignment. So you can just fill in the answer. Now, examining the diagram here, you have two bullet holes through glass. Which one came first and why?
B came first because the entry hole is smaller.
Okay. But why would the entry hole have anything to do with it?
I would say A came first because by looking at the lines, the radical cracks, A has like lines that go across, while B, it kind of stops. So since one crack can't pass through another crack, I think A came first and B stopped because it couldn't go through the cracks of the A.
Exactly right.
Okay.
Very good. You look here and here, you'll see that the cracks from B stop at A. The length of the crack has nothing to do with order. The length of the crack simply has to do with the characteristics of the glass, the molecular structure, whether that would allow that crack to go so far. To do order, you simply look at the radial cracks, noting that a pre-existing crack will stop all others. Okay? Then here you have a series of bullet holes. Is this sequence possible? Why or why not?
Oh, sorry, because you have cracks
Why
going
not?
into the cracks are overlining.
I didn't understand it. You just said. Try again.
Oh, okay. Cracks are overlining. There's some cracks that are overlapping.
Okay. I don't know whether it's your internet or mine. I every once in a while I get this thing that comes up on my computer that says my internet is unstable. Like, okay. I have
Would you like?
moved. No, I heard you. I got you. I heard it.
Okay.
Okay.
Oh, okay.
So
Okay.
we have cracks here in particular, and here that the radial cracks appear to travel through the concentric cracks, and that cannot be. So this sequence is not possible because of that, and particularly just the B is the problem. Okay. So B is the problem. So then the last question is, which one came first and which one came last?
I'm not sure why, but I want to say A came first, and possibly D came last.
Well, what are you looking at?
I don't know. I guess for A, I would say the size, but I'm not sure if that has anything to do with it, really.
Well, we know cracks can't travel through pre-existing cracks. We also know that a pre-existing crack will stop another crack. So look at the cracks on who stops who.
Would it be C?
First or last?
To be the first crack?
Because
Because of the radical crack is stopping another radical crack of A. Same with B
radial.
and sorry,
They're
yeah,
not
radial.
radicals. They're radials. Radical means like, crazy. Yes. So looking right here, up at the top, if you look here, C's E, D is stuck in the
Sorry,
middle.
Professor. You
So
cut out.
So therefore C. Go ahead.
You cut out for a second. Oh, the last thing I heard was A and C, and then you said E.
The crack he sees, A. The crack here from C stops both B and E. E at this point as well. So therefore C would come first. E, well, who's last then? Which one was the last one fired?
D,
D?
because Because
Because E stopped all of the transmission of their cracks. Yeah.
I'm sorry, could you repeat that? You cut out.
D had to be last because E is all held in E. All the concentric and radial cracks of E stop D from progressing anywhere. The likelihood of E occurring after D is highly unlikely.
Professor, can you repeat your reasoning for why D is last? I'm sorry, you kept cutting out. I couldn't hear properly.
Because it's completely self-contained within E. Therefore, E stops the progression of all of the radial cracks from D.
Okay, that makes sense. Thank you.
Okay? All right. Now, part B. Part B, we have a series of pieces of glass that were recovered from different places. And first we have a piece of the window that was collected and then recreated. All of our specimens came in small manila envelopes. It says that on your instructions. So I want to remind you, whenever you do any analysis, the first thing you do is write an identification of that item. So that is a description, which includes the packaging. Be very careful on some items of what you call it. You have to be cognizant of the fact of things that you can state what it actually is versus some things that you cannot. Now, glass, you can call it glass because there's no ifs, ands, buts with that. Right? Blood, for example, remember you can't call that blood. It's only a red stain. So, this is specimen number one. Specimen number one, it was in a small manila envelope. So we would start out with number one is specimen number one. A small manila envelope containing. Right. So what do we have here? We have 1, 2, 3, 4, 5, 6, 7, 8. 8 pieces of glass from a window at the scene. At the end of your sentence on every description, you must state its source. Where did it come from? Not who you think it belongs to, but where it came from. Where was it found? Right. So now describe this, your specimen to me as best you can. Being that you don't actually have the glass in front of you. How would you describe this glass?
I would describe it as rigid on the corner pieces.
Describe the glass first.
Oh,
Clear.
Color. Color.
Clear.
Well, clear is actually its transparency. Color is that it has no color. You understand the difference?
Yes.
Actually, it does have color, but you can't see it. So we'll go with the no color. It actually has a green tint to it, but the green tint is red. It doesn't come through on the photograph. So we'll go with no color. Transparency is that it's clear, because you can have glass that is transparent. It can be translucent, or it can be opaque. This is transparent, which means you can see through it. You have at least some scale of measurement there. Okay. You only have two edges. Two of your edges are manufactured edges because they are perfectly straight. So you know this is a corner of the window. You're going to have to extrapolate based on the measurements that are there, the approximate measurements of the other four sides, because we do not do length and width. We have to actually measure the perimeter of all four of these additional sides. Okay? So you have a ruler there for scale for you. If you were to have this PDF, it's not going to change for you. Have it at 100%, then you can or adjust the percentage so that the ruler matches exactly what a ruler is, and then you can measure the rest of the sides. Okay, so make it smaller, zoom it down so that the ruler actually matches a real ruler, and then you can measure the other four sides. Okay. I will tell you that the thickness of this glass is 2 millimeters. So we have that the glass is 2 millimeters thick. It is clear. It is transparent. Well, it is transparent. No color. Has manufacturer edges on two sides, forming a corner. The other sides, one comes to a V shape, and the other two are, one is straight, one is slightly curved. Okay? Then we're going to look at specimen number 2. Specimen number 2, small manila envelope containing a piece of glass recovered from, and I don't remember what it was recovered from. It says on your actual handout. There's specimen 2, I believe, came from just the scene. Specimen 3 is found on the suspect. So we'll go with that. So specimen number 2, a small manila envelope containing a piece of glass found, I believe it's outside the scene. Could be. Whatever it says, go with it. Right, suspect. So now describe this specimen.
No color, transparent, triangle shape.
Triangular shape. Does it have a straight edge?
Yeah.
It does. Size of the ruler.
And would the thickness still be the same?
It is 2 millimeters thick. Okay, I found my paper. Specimen number 2 is a glass fragment covered from the suspect's pants, so it's suspect item. So that's our identification. We have a couple of chips on the lower right-hand corner, opposite the manufactured straight edge. The fact that it has a straight edge is important. You will see that shortly. Then we have number 3. Specimen number 3 is a small manila envelope containing a glass fragment recovered from vehicle suspect. Describe the specimen for me.
Would you describe it the same so it would be clear, no color, 2 millimeters thick?
Yep. Now, you did great, okay? No one ever said to me that it looks like specimen 1. Okay? You have to stop using the word also, because if you were to say it also is, that's a comparison. And you can't do that. Okay? Every specimen is an entity unto itself. While it may seem like you're repeating yourself in the description, you are. You have to. Okay? You must describe every entity, every specimen, all by itself. You're not doing any comparisons yet. Okay? So we have to know exactly what does this specimen look like. It's 2 pieces of glass. It was 1 until about a year ago. And then somebody in one of the classes dropped it and then broke it. Okay? So it's 2 pieces of glass that obviously can be fit together. Okay? We have a straight edge, which is the edge where the ruler is on the left. Okay? So we have 1, 2, 3, 4, 5-sided piece of glass. Clear, transparent, no color, 2 millimeters thick. Okay. One of the edges appears to be a reverse V pattern. One side is angled and one side has a curve to it. And of course, one side is a straight edge. Those are all your descriptions of this particular glass. So now what we're going to do, because the purpose of this lab is physical patterns, not identifying the glass, which we would do eventually, we are now going to bring them together. So this is the only time you can bring specimens together if you don't run the risk of damaging the specimen. We're not going to damage glass by putting it together. Okay? Tool marks we would damage by putting the tool in the mark. So you have to be careful what things you bring together. Okay. So, specimen number 2. This picture has 2 and 3 together. I don't know why I did that. So, specimen number 2. The question on your lab report is you have a choice with both specimens. You have to make a statement. Okay. Well, first we've illustrated them together. Did specimen 2 originate from specimen 1? So your choice is it did originate, it did not originate, or it is inconclusive. Now, in the scientific world, inconclusive means maybe. It doesn't mean no. It doesn't mean yes. What it means is I have some information that makes it possible. So it's not a no, but I don't have enough to say yes. So I'm going to leave it at the possible. And our word for that is it's inconclusive. So what is your opinion as to number 2 originating from specimen 1?
I might be completely wrong, but I don't think it came from specimen 1.
Is it a did not, or is it inconclusive? Is it a possible?
Yeah, maybe I think it might be inconclusive.
Okay. Because could it have come from that window?
Yes, but it could have. I just think we're missing another piece that would match in between the two. So I'm unsure if it.
So the reasoning. So what is the characteristics that bring you to possible rather than no? What are the similarities?
The fact that it's no color, that's the one thing that we can match, but we cannot match the shape. I cannot link sample number 1 with the rest.
Okay. The inherent characteristics of the glass are similar. Same transparency, same color, which is none, same thickness. Okay. Texture we could also do, but you don't have it to touch. Okay. So all those characteristics are similar. We cannot physically fit it back because, as you can see, the number 2 there is positioned so that the straight edge is parallel to the other straight edge. This is a straight edge. You can't angle this piece in because this needs to form a square. So it could have come from this window, but I don't have enough pieces. I don't have enough information to say that it did. But because it's the same type of glass, I'm not going to say no. So that's why it's inconsistent. Okay. Now, number 3. What is your opinion for number 3? It's a better picture.
I would say that number 3 came from the window, and it's a match because it not only is in like the same color, the same basic principles, but also creates a good match with the straight edge as well, and put together it looks like it came from the same piece.
And the physical pattern method you're using is?
Would you discuss the curvature of the glass and how it matches that way?
I could. We have an inverted V and then we have a V. And the inverted V of number 3 fits, fits into the V breakage of number 1. So we have it physically fitting back together. Is that not a comparison process? Physical fit, yes?
Yes.
It is. Doing direct matching, physical fit, is a comparison process. For number 2, we used indirect matching because we could not do physical fit. We can't get it to physically fit. But the inherent characteristics of the glass are similar. So that's why it's could have. In my world, things are not always yes and no. We have a whole lot of could haves. We have a whole lot of possibilities. Okay? So it's much easier to eliminate anything. If it doesn't look like it, it doesn't fit, it's easy to eliminate. It's very difficult to get to the definitive yes. Most of the time we're in the middle. And then we have our likelihood that it did or did not come from that window. And that's where a lot of our opinion falls in. Okay? So 2 would remain just a possibility. We would have to do further glass analysis to determine that. But even still, it would still only be a possibility. We could never get to the point of saying, yes, it came from number 1. 3, we can say, yes, it came from number 1 because we did a physical fit. Okay. So now on your lab report, there were questions. Where's the point of impact? Because we can leave 3 together with 1 because we've now determined they came from 1. Where's the point of impact?
Where all the
On the
corners.
opposite side.
One at a time.
On the opposite side.
I'm not asking you from which side it came from, just looking at that glass.
The center where all the radical marks, radial marks are coming from.
Think like your tires. You have radial tires. There's no C. That's okay, I'm teasing. Yes, okay. You have a point here where all your radial cracks meet. That's your point of impact. Okay? So you don't always have a hole. When you have a bullet hole, you have a hole. If you had this glass in front of you, there's no hole. All of those pieces of glass actually meet together. There's a very little chipping at all. They were just struck with a hammer thing, to fracture the glass. So we put it together where all the radial cracks, they all radiate outward from the point of impact. So we can see all these cracks radiate out from a central point. So the central point is our point of impact. Right? So now, if you had the glass in front of you, if you were to pick up one of the pieces of glass, you could look for that angle to the glass, right? And you would, looking at the angle here, this would be the smaller side because the glass would all come together. So this is the large side of the cone. So then we could make a determination that this glass was fractured from this side. Maybe. Okay. Glass is inherently fragile, and it's going to continue to break if it falls. It could be just that the actual instrument itself chipped the glass in that area more than others. So while you could do this, I wouldn't rely solely on it. Okay? So now what we need to do is we need to look at a radial crack. And you have to make sure it's a radial crack because, for example, this up here is not a radial crack. That's a subsequent breakage to the glass because it fell. Okay? These, and see this one here? This is actually not a radial crack. It doesn't come to the center. It actually comes to right here. That's another piece that a student broke. So if we were to look at one of these large radial cracks and we look inside the glass, we would see this. So you see these waves on the edge of the glass. And mind you know how hard this was to get the picture of the side of the glass? I had to get a macro lens on my phone to get that to work. Regular camera wouldn't do it. Ordinarily in the classroom, some of the microscopes, 2 of them for the professor's use, hook up to a camera and we could project this onto the screen. If we had known we were going pandemic, could have done all of this before we actually got it. So I did it on my own. Okay. So looking at this glass, we now have these lines that come in from this side of the glass, swoop across, and come down. Come in from this side of the glass, go across, and come down. The actual point of impact is down the bottom here, because remember, this radiates upward from the point of impact and then goes across. So what are these marks called?
Hackle marks.
Hackle marks, that's sufficient. Now, what is the 3R rule?
Radial cracks form right angles on the reverse side of the force.
That's correct. So now, using the 3R rule, from which side was this glass fractured, the left or the right?
The left.
The left. Very good.
Professor, can you just explain how Nivu got the answer? Because I'm just not getting that.
Okay.
Or if you could explain it, Nivu, because I'm just, maybe it's my screen, but I literally cannot see any, like, those cracks that she was describing.
Well, the way I see it, you see how it like forms in a lowercase r and how it like goes out.
Okay.
So if you like turn it up, like turn it around, you kind of see the picture that the professor drew. So the right angle would be on the right side. So the opposite of that would be the impact, if that makes sense.
So that the lines come in and go down. Some of them are wide, some of them are not so wide. They go in like this. Okay. So looking at this picture, they come in here. You can see a line here, here, and here. I enlarged it so hopefully you can see it better. So it comes in here, swoops across, and then goes down this side of the glass. This side comes in, swoops across, goes down the left side of the glass. This one here comes in, goes across, comes down the left side of the glass. So this edge of our glass is one side of our right angle that we have here. The other side of our right angle is the actual hackle mark coming in. So this is one side of our right angle, and then this is the other side where it comes in. So then, if this is the right angle, the 3R rule says the right angle is on the reverse side of the force. So if this is the right angle on this side, therefore the force had to be on the left. Or the back side of the curve. Some people like to remember. Okay? That make it better for you?
Yeah, it was a lot better when you enhanced the picture and made it bigger, because I was not able to see it before. But thank you.
These pictures are on your module, so you can look at them again as you're finalizing your lab. Right? They're all there for you to see. All right. Then part C, this one you can do on your own. This is really simple. Okay. Part C, we have a hit and run. We have two specimens. We have a shirt from the victim. Okay. And we have, there you go. We have, first of all, here's the shirt. So specimen number one this is a brown paper bag containing a pink with green and white plaid pattern shirt. B for victim. That's your identification. Okay. Now you're going to describe the shirt. Don't care about it. You could say long sleeve. You could say it's got a collar top. Don't care. None of that is relevant. What is relevant in your examination of the shirt is the back of the shirt. So in your description of your specimen, you were going to describe the back of the shirt, the fact that there is a hole torn in the shirt. And there's an enlarged photograph of the hole. Now, what you see underneath the shirt is a grid pattern. It's this thing. And each individual grid is a centimeter. So you can measure this in centimeters. I know I usually tell you to do inches, but centimeters is okay because this makes for a lot better photographing. So you can actually count the centimeters of how exactly big this hole is. Okay? And then you have specimen number 2, which is a small manila envelope, and it states that on your instructions. Small manila envelope containing a fragment of cloth recovered from the undercarriage of the car. Suspect. Source goes at the end of the sentence. Then go on to describe this specimen, that it is pink with a green and white plaid pattern. Don't compare it to number 1 yet. Okay? And it is on this same measuring grid so that you can get all the dimensions of all the perimeter sides of the fragment. And then we'll bring them together. And here you have specimen 1 and specimen 2 brought together. And the question is, did specimen 2 originate from specimen 1? And why? And what is the comparison process you used to determine that? So that's your really simple one. So did 2 come from 1?
Yeah, yes.
How many will put their hand on a Bible and say yes?
I'm good.
And your method of comparison would be?
The pattern of continuity, the white line, the white strip, and also the green plaid.
Mm-hmm. Absolutely correct. Indirect matching using continuity of pattern, because you don't have a physical fit. A little bit on this side, but that's not sufficient to be able to say yes in court. Rely on the inherent pattern of the material itself, the fact that you have one edge fit nicely, the pattern continues from one to the other, back to the other, so we go from specimen 1 to 2, back to 1. Classic continuity of pattern. Okay? So work on that.
Oh, I'm sorry. Would that be inconclusive or would that be a full-on yes?
Oh, no, that would be a definitive yes.
Okay.
Indirect matching gives you an absolute match. There's no 2 things tear the same way. No 2 things can have those same characteristics. The same. Okay? All right, I've put up a discussion board on physical patterns so you can all discuss your lab. Please participate in that discussion so you can get points for it. It doesn't really matter what you say, just as long as you participate. And we're having a quiz on physical patterns Friday. You can take it anytime after this class, before Friday. If you don't take it by Friday morning, then we'll take it actually on Friday morning. Okay?
I have a question.
Yeah?
Did you happen to delete the handwriting module? I can't see it on my modules.
Did I assign that to you?
No, I was just, well, we talked about it.
Yeah,
I don't think I ever assigned it to you. Right? Yes? No?
It was an assignment that you had us hand in. It was an assignment, but now we can't see it.
Okay. All right. Let me check that. It may have gotten. Who knows? I may have. I'll make sure it's there.
Okay, so I just wanted to let you know in case, because it's due today, but it's not there, so. Okay, thank you.
Okay. Yeah, that, okay. All right, then I was on Friday.